The electric potential is closely associated with the energy of a system of charges. On the screen we've got a positive source charge and a small little test charge in its vicinity. Due to the Coulomb interaction between these two charges, we know that the test charge will be pushed away from the source. Let's look at the motion of this test charge over a distance L, as is shown. We know that the test charge is pushed away by a non-zero force, which means that it accelerates, so it gains velocity. This implies that the system gains kinetic energy if we assume that the source remains stationary, and as this is an isolated system, it also implies a certain drop in potential energy. And we want to figure out how much kinetic energy is gained by the test charge moving over the distance L, and how much potential energy is lost by the system for the same motion. In order to answer this question, we need to calculate the amount of work that is being done on the test charge. The work in this case is being done by the Coulomb force, which is an internal force. However, it's not a constant force. Therefore, in order to calculate the work that is being done on the test charge, we first look at a tiny little displacement, dy. If we choose dy small enough, we can approximate the electric force acting on the test charge as being constant over that small displacement, which means we can write down an expression for the work done on the test charge for the tiny infinitesimal displacement dy1. Furthermore, we know the electric force is just given by the test charge multiplied by the electric field produced by the source, so that we can write the work done for the tiny displacement dy1 as the expression that is shown. By looking at the work done for all the tiny little displacements between the start and the end point of the motion of the test charge, we can get an expression for the total amount of work done as the test charge is displaced over this distance L by the electric force. As this is a sum of a number of infinitesimally small quantities, we can write this as the integral that is shown at the bottom of the screen. In this example, we have chosen a very particular path, one that lies parallel to the vertical axis. And since we know that the electric field produced by a spherical source is radial, it means that for this path, the electric field everywhere along it will also point in the vertical direction. This means we can simplify the integral describing the work done on the test charge as follows, where the dot product just evaluates to unity. Therefore, we can calculate the amount of work done as this expression in terms of purely the start and the end points of the motion of the test charge. From the work energy theorem, we know that the total work that is being done is equals to the change in kinetic energy of the test charge, and this is equals to the negative of the change in potential energy of the system. Therefore, the change in potential energy of the system is given by this expression, which depends on the test charge, the source charge, and 2 points in space. This naturally leads us to a definition of the potential energy of the system at a particular point with respect to the source. Note that this expression goes to 0 if the test charge is infinitely far away from the source. This means if the test charge is infinitely far away from the source, it has gained its maximum amount of kinetic energy. We can divide this expression for the potential energy of the system of these two charges by the test charge itself, which gives us a quantity that we call the electric potential. The electric potential basically depends on the amount of charge carried by the source, but it maps a value to every point in space around the source. So a scalar value is assigned to every point in space around the source. The meaning of these values is that it is the amount of potential energy that this system would gain if a charge of 1 Coulomb were to suddenly appear at that particular point.